Hi, welcome to our presentation of masked supervised learning for semantic segmentation. To begin, we start by motivation where we talk about the problem and discuss the limitations in previous work. We then describe our proposed method in detail. We also show experiment results with comparison to recent approaches, as well as conduct ablation and robustness studies. Finally, we will end with a conclusion. The basic goal of semantic segmentation is to classify each pixel in an image into a predefined semantic category or classes. Its real-world applications range from medical image analysis to robotics. Semantic segmentation is still a challenging problem due to a number of reasons. First, there is a diversity in the size and texture of the regions of interest or ROIs. Second, the same type of ROIs may have different sizes and colors due to the label acquisition protocol. Moreover, there are cases of ambiguity where the boundary between the ROI and the background cannot be easily distinguished. Third, in cases of natural scenes, there are multiple class instances which are cluttered together, and there also exists imbalance in these semantic classes. There are also different lighting conditions, making the task much more difficult. Previous works on semantic segmentation include FCN and UNet, which are convolutional-based encoder-decoder networks, and have been further extended for improved performance. Some recent works have also demonstrated that modeling long-range context, typically via self-attention mechanism, translates into better segmentation performance. Further, methods have also been proposed that does not explicitly leverage context, such as self-supervised masked autoencoders. In this study, we figure out if short-range context is helpful and how does it work with self-attention based methods for semantic segmentation. While self-attention is of vital importance in semantic segmentation, as it enables modeling of long-range context, which translates into improved performance. However, most of the self-attentive methods for semantic segmentation tend to over-segment ROIs, output noisy and discontinuous predictions, fail to accurately predict the boundary regions, and poorly segment minority class. Moreover, they tend to yield misclassification in multi-class image segmentation due in part to the imbalance that exists between the semantic classes and the large number of semantic classes. We argue that short-range context is equally important to predict small ROIs in medical images, as well as to accurately segment ROIs and reduce misclassification of minority classes in images of natural scenes where the class instances are dense and cluttered. To address the above limitations, we propose masked supervised learning, a novel single-stage learning paradigm for semantic segmentation to effectively learn rich and discriminative representations. MaskSup follows a Siamese-style network where the two branches are identical and share weights. Given an image and its randomly masked image, MaskSup models short-range context among neighboring pixels as the context branch is tasked to predict the semantic classes of the masked pixels, thereby leveraging information from non-masked pixels. MaskSup also models global or long-range context by a task similarity constraint where the similarity of the outputs of the two branches is maximized in order to better learn the shape of the class instances, which is especially useful in multi-class semantic segmentation. Here we show an overview of masked supervised learning framework for semantic segmentation. This method follows a Siamese-style network in which the segmentation branch and context branch are identical and share weights. Given an image and its randomly masked version, we employ a base segmentation network to output the predictions, followed by computing an overall loss function. We use a loss L context to learn short-range context among neighboring pixels as the branch predicts the semantic classes of masked pixels by leveraging information from the non-masked pixels. We also use a loss term L task sim to learn long-range context as the similarity of the two outputs are maximized. and hence enables us to better learn the shape of the semantic classes. Overall, MathSub enables better representation learning for semantic segmentation by capturing the contextual relationship between pixels by predicting a segmentation map for the masked version of the input. MathSub can tackle cases where the regions of interest are ambiguous at boundary, various scales, shape, appearance, and also for images that have multiple class instances with imbalance, resulting in fewer pixel-level misclassification of minority classes. During training, the loss L total is minimized over several epochs to learn the parameters f theta using a label training set. After training, we employ the network f theta to infer a new image that outputs a prediction mask. It is important to mention that at test time, the images are not masks, and random masking is only used during training. In the first plot, we show predictions on medical images. Notice that there is a change in the overall shape and appearance of the glands. The baseline methods tend to over-segment the regions and also produce noisy outputs, as they fail to capture the global structure and semantics of the glands. The second row shows the cases of ambiguous regions of polyps where the baseline failed to accurately segment the ROI. This is largely attributed to the limited capability of the learned representations used in the baselines. Interestingly, the Levitt unit baseline fails to segment ROIs that are ambiguous at boundaries and vary in size and color, even though the transformers are quite strong at modeling long-range context. Self-attention can be regarded as a form of non-local means, and it captures long-range dependencies, resulting in over-segmentation. The bottom plot shows that the baselines fail to accurately segment multiple class instances and output discontinuous predictions and misclassify instances. In the last row, we see that the baselines fail to segment the minority class. Overall, they fail to capture the context of target regions, resulting in over-segmentation, noisy and discontinuous predictions, as well as misclassification of instances, leading to unsatisfactory predictions. By comparison, MathSub is able to better capture the shape and appearance of the instances due to the context branch, which models short-range context among pixels, resulting in better representation learning. Moreover, the task similarity constraint leads to long-range context invariance, enabling MathSub to better learn the shape of the ROI, which in turn translates to better predictions. Overall, learning with context branch and task similarity constraint helps in cases of segmenting ambiguous ROIs at varying size and color, and also better segment minority class instances in cases of multi-class segmentation. Quantitatively, we find that MathSub improves performance by 5% on multi-class semantic segmentation of natural scenes. On medical images, MathSub outperforms recent state-of-the-art methods such as medical transformer and Levitt unit. In addition, MathSub outperforms MTINet, which is a relative improvement of 5%. This is significant because MTINet is a multitask learning method that jointly learns 4 different tasks and requires additional annotated data for training. In contrast, MathSub only requires images and the pixel level annotations, segmentation masks, thereby reducing the need for intensive manual labeling of additional data. The results demonstrate the effectiveness and capability of MathSub in modeling short and long-range context, yielding improved segmentation. MathSub also outperforms self-supervised masked and autoencoders, even though May is more computationally expensive and enjoys longer training time. We also perform ablation experiments to quantify the effectiveness of context branch and task similarity constraint. We find that the context branch leads to better modeling of local semantics and is tasked to output pixel-wise predictions for masked regions in the input, thereby leveraging information from neighboring pixels. We can see that the context branch improves performance of different segmentation methods across the 3 datasets. This shows that MathSub is generic and can be easily integrated into any existing segmentation method. However, it is important to mention that a higher performance improvement is observed when the architecture is a transformer-based method due to its key characteristic of modeling long-range context. We also find that the task similarity constraint further improves performance of both convolutional and transformer-based methods. This use of the task similarity constraint results in learning long-range context invariant representations which help to capture the shape of the ROI. This in turn leads to accurate predictions even in cases of different shapes and appearances of instances, ambiguous ROIs at different sizes, and imbalance among multiple class instances in multi-class segmentation. Ablation study of high and low masked pixels regions during MathSub training shows that masking the images heavily during training yields better performance of MathSub across the all datasets. Here we show the robustness of MathSub to mask corruptions. As can be seen, MathSub is able to predict the ROI even when a large portion of the image is masked, demonstrating the capability of modeling short and long-range context by better segmenting both small and large ROIs. Using both context branch and task similarity constraint, MathSub is better able to learn context invariant representations to better segment and preserve the ROI shape. We also show that MathSub is computationally efficient without compromising segmentation accuracy in compared to scale version of the networks. We introduce a masked supervised learning approach for semantic segmentation that can be easily integrated into existing methods. For future work, we aim to investigate what type of masking strategies work best and also apply MathSub to other computer vision tasks.